Now let's try to find the solution of a linear homogeneous recurrence relation. Now, a linear homogeneous recurrence relation can be generally represented as an is equal to c times 1 c1 times a n minus 1 plus c2 times a n minus 2 plus c3 times a n minus 3, so on to ck times a n minus k. Now this is called as linear homogeneous recurrence relation, because if you look at this equation or relation, you have a constant multiplied to each term. There is C3, C1, C2, so on to Ck. So that's why it's called as linear. It's homogeneous because in each term you will find A. So here we'll have A, here is A, here is A, here is A. Then the degree of the equation is, or the order is represented by how many steps you have taken back. So this means 1, this means 2, and this means 3, and n minus k means you have taken k steps back, so the degree is k. Now, if you have to find the solution of this linear homogeneous recurrence relation, then let's represent that with an is equal to r raised power n, where an is our recurrence relation and Rn is a solution to the recurrence relation. So we say that this is the solution to this recurrence relation only when this entire thing, this equation is equal to Rn, which is equal to C1 times R raised power n minus 1 plus C2 times R raised power n minus 2 plus C3 times R raised power n minus 3, so on to Ck times R raised power n minus k. Now, if you do a little bit manipulation of this, if we divide the both sides of this equation by R raised power n minus k, divide this part also by R raised power n minus k, then what we get is, after the manipulation, what we'll get is Rk minus C1 times R k minus 1 minus C2 R raised power k minus 2 plus so on to Ck minus 1 R minus Ck is equal to 0. So we are basically dividing both sides by R raised power n minus k. If you look at this part in particular, this will become R raised power n minus k. So this will be R raised power n minus n plus k. This and this will cancel out, and that's how we got this. And that's how we obtained this part, also by dividing we obtained this part by dividing r raised power n minus k, and this became c1 times r raised power k minus 1. Now this entire thing is called as the characteristic equation. And the roots that we obtain of this equation are called as the roots obtained, are called as characteristic roots. Now, if let's say we have a linear homogeneous recurrence relation of degree 2. So if we have a linear homogeneous recurrence relation of degree 2, and let's say C1 and C2 are real numbers, and let's say this is the recurrence or the characteristic equation. So since the degree is 2, therefore it will be only this big. Then since this is quadratic equation, it will have two roots. Let's call them R1 and R2. Then AN is a solution to the recurrence relation AN is equal to C1 times AN minus 1 plus C2 times AN minus 2. So this is basically the same equation that represents the recurrence relation, the linear homogeneous recurrence relation in a generalized way. So since the AN was here as a general number, but here AN, the value of n in this case is 2, so we'll have only two terms, n minus 1 and n minus 2, and hence degree is 2, and its characteristic equation will be this one. This is its characteristic equation, and this is the recurrence relation. Then this will be solution. AN is a solution to this recurrence relation, given that the characteristic equation is this one, R2 minus C1 times R minus C2, and at the same time we know that the two roots are R1 and R2. So this will be solution to this recurrence relation if and only if AN is equal to alpha 1 times R1, which was the root of the characteristic equation, plus alpha 2 times R2 raised power n, second root to the characteristic equation. And here n ranges from 0, 1, 2, and so on. And at the same time, alpha 1 and alpha 2 both are constants. So more of this will become clear with some examples. So this was a general representation. This is how we represent a linear homogeneous recurrence relation in general, where the degree is, let's say, k, because we have taken k steps backward. So in this case, the degree was 2. So 2 steps were taken backwards, n minus 2. and this was its characteristic equation which had roots r1 and r2. Then in terms of that, if we have to represent the solution of the this equation, then we'll have c1 and c2, and this will, in terms of that, in terms of the reconciliation and the characteristic equation, will have an is equal to alpha 1 times r1 raised power n plus alpha 2 times r2 raised power n. So more of this will be clear with examples, which we'll be discussing in next video.